Welcome to session PRS 311. I'm Rudolph Balaz. I'm the program manager for Direct 3D 9 on Windows Vista, and I'd like to welcome you to this session. I see there's still a few people coming in, so hopefully we'll have everybody in by the time I'm finished with these introductory slides. What I wanted to do to start off is just do a quick survey of the audience here and find out, a couple of things from you. How many people here are really familiar with 3D graphics? More than half of you. That's really good. So how many of you are currently using D3D? Pretty good. And so I'm guessing you're all here to find out what's going to happen in Windows Vista. So let's look at the two talks we have actually scheduled for this afternoon. This talk, I'm not going to be doing any demos in this talk. We'll be looking at a little bit of API definitions. But mostly what I'm going to try and cover in this talk is the changes that have happened to the graphics stack. We're really going to focus on things like what are the underlying changes in Windows Vista, what are the new APIs, new capabilities, how those are exposed to you. When I was actually putting these talks together, I think I started off with something like 190 slides and managed to somehow whittle it down to 40. So it's going to be pretty condensed, and there's a lot of information here. The second talk is really a follow-on, and the hard part we had balancing between the two talks is where we put the demos. So we wound up putting all the demos into the second talk. In the second talk, we're going to start off with introduction to shaders, to D3D 9 for current technologies. And so for those of you who haven't used D3D up until this point, it will be a good introduction in seeing how you'd actually build an application. We'll start off building a world application. The second half of that talk will then move on to talk about D3D 10, and we're actually going to do a particle system demo walkthrough and how to use the GPU for something that's not necessarily rendering, but actually is other types of calculations. So hopefully as you listen to both of these talks, you'll find that there's a little bit of everything in here. There's information for people who may not be as familiar with D3D, as well as information that's going to be critical for those of you who actually currently are using it and have applications that are going to be running on Windows Vista. So with that, I'm going to talk a little bit about what I'm covering. The hard part about organizing this particular talk was there's really two different things I want to talk about. One of which is the goals that we had for the graphics stack in Windows Vista and how we went about achieving them. This sort of thing is typically an architectural discussion with a lot of diagrams saying where the pieces fit together. The problem is that it also spans a lot of technologies. So it was kind of difficult organizing the slide deck. So I picked an organization that will sort of jump between these two goals as I go through the talk. I'll be talking about the new display driver model in Windows Vista, how that works, what the implications are in the infrastructure. And then I'll talk about the actual API modifications and changes in behavior for Direct 3D 9 and Direct 3D 10, which is the new API set coming out. For those of you who aren't as familiar with Direct 3D, the main purpose of Direct 3D is to get direct access to the hardware. We're really talking about applications that need the raw power of the GPU, that you need high frame rates. Your applications are going to be highly graphical intensive. These could be games. They could be workstation applications like CAD and so on. But they're also the newer classes are things like productivity apps are now starting to incorporate 3D into various aspects of themselves. Now, Direct 3D, currently, as it ships today, we provide an SDK that has both native and managed API sets, a bunch of tools for various different types of activities for doing your 3D applications. And we'll talk somewhat about those in the next talk. So with that, I'm going to start with the architecture diagram. This one's probably slightly different than the other ones you've seen today in Windows Vista, because I'm going to start from the bottom up. And a fair portion of this talk will be focusing on the Windows display driver model. These are the underlying changes both to the device drivers, to the graphics infrastructure, the kernel changes, as well as some of the things that have moved out of the kernel. On top of that, we have the Direct 3D runtimes. We have Direct 3D 9, which most of you those of you who have used D3D are familiar with. as well as a new runtime coming for D3D10. I realized after I put this slide deck together that what I did was I left out some of the legacy APIs. There's a bunch of other D3D API sets available as well, things like D3D7, D3D6, DirectDraw. Those are all still supported on Windows Vista, but for this talk I'll be talking about these particular sets of APIs in general. Now, no diagram of the graphics stack is complete without adding in all the other pieces. The boxes in gray I'm actually not going to talk too much about during this talk. Things like D3DX, which are the utility libraries that are used pretty well by all applications that use Direct3D. The Windows Presentation Foundation that you've had probably gone to other sessions on today. And we have some other tools and libraries, things like the effects system in D3D. I won't be touching on those ones in this particular talk, but they all form part of the graphics stack and are used by applications to do their 3D graphics. And the last piece I will be touching on is your applications and the desktop window manager. Because there's as you can guess, there's a pretty tight correlation between the desktop Windows manager and the underlying runtime, since both the desktop window manager for Windows Vista and the Windows Presentation Foundations are all built on top of D3D, and there's some interesting implications for your applications there. So with that, I'm going to be going through, and you'll see this pattern repeated throughout the slide deck. I'm going to be talking about subtle changes in the OS, things that have been modified, as well as things that you as an application developer need to do to either compensate or work with those things. The very first one, and this is sort of a fallout of the new driver model, is that GDI, for those of you who use GDI heavily in your applications, along with your 3D, along with other things, GDI in Windows Vista will be software-only rendering. It's not if you're using the new driver model. It won't be using hardware accelerated. So on Windows XP today, for example, when you run your application, you get some level of GDI acceleration. On Windows Vista, if you're still using the old driver model, you're using an old driver for whatever hardware you happen to have, GDI is still hardware accelerated in those cases. But when you go to the new driver model with the new features and new benefits, one of the things we had to give up was the hardware acceleration of GDI. I believe in most cases this should be okay, because you're going to gain benefit from the composition engine. You're going to be compensated by a lot of other things. The next big subtle change is composition itself. I don't know if you've had time to think about what the implications of composition may mean to your application. The piece that's probably going to cause you the most time in terms of looking at problems or issues is some timing may have changed. Window messages may arrive at slightly different times from when you expect them. You may actually be getting other window messages than you expected. And this is part of composition. In some cases, you may not be getting window messages that you used to get under Windows XP. For example, you may not be getting paint messages when a window passes over another one of your windows. Thank you. I just got handed a note saying overflow to room 511A. So if anybody wants to go to the overflow room, it's 511A. And so these are pretty straightforward things that have changed, and as soon as you start working with Windows Vista, you'll probably start noticing them. I'm just pointing them out ahead of time. Now, a different thing that happens with composition has to do with application compatibility. Obviously, Windows Vista has to be backward compatible with a fair set of applications that are out there today. And there's a bunch of things that you could do in older APIs, especially the older D3D APIs like DirectDraw, that we really don't know what your intentions were when you actually call those APIs. So for example, if we look at GDI, in GDI, if you actually go to the platform SDK, there's a sample that shows you how to copy the desktop to a bitmap and save it to a file. Well, that application, what it does is it does a get DC null. Well, get DC null allows you to not only read the screen, but also write to it. Well, as soon as that happens, one of the things we have to do is turn off composition, because we're not sure what you're going to be doing. Remember, composition is actually taking separate buffers for each one of your applications, pasting them all together. Well, if you're doing a get DC null and getting the actual GDI surface, we don't know you're going to be writing to it, so we have to stop doing that process, and so desktop composition turns off. The glass experience will disappear. Your users will probably notice that composition has disappeared. So If you go home today, you may want to go and look and see where do I use get DC null in my code. Some people use get DC null just to get a compatible DC, which is okay, but it's going to remember the side effects. Direct draw has a similar sort of thing where you can lock the primary. That'll turn off composition as well. Anytime you're going to try and access that front buffer that's being scanned out, you're going to have this effect. And the last subtle change when you're talking about the new driver model is we're going to be shader model 2.0 baseline. So if you are running on Windows Vista and you have glass and so on, at the very least you can make an assumption on terms of what the hardware is capable of in that sense. So this is the second pattern you're going to see throughout the slide, is things to do. You know, obviously the very first one is don't lock the front buffer, whatever you can do. And now that you all have the release from the PDC, please go install it, try your applications, see if you're doing anything that may interfere with composition. There's actually some fairly well-known applications out there right now that I'm working with the vendors to try and, correct for whatever reason they're doing things like locking the front buffer and turning on off the desktop composition. Another interesting thing, those of you who have looked at the Direct 3D samples we ship into DirectX SDK, all of those applications are written to render as quickly as possible, because the whole thing about Direct 3D is it's about high frame rate. Well, if you're running in windowed mode under desktop composition, the desktop composition is only happening at maybe, 1/60th of a second? So there really isn't a point to be rendering 1,400 images before it actually displays on the screen. What all you're really doing is, if you're not throttling your rendering, is you're using up GPU cycles and other system resources that you could use for something else. So when you're in windowed mode and you're running on Windows Vista with composition, please make sure you throttle your rendering so you're not rendering, more frames than are absolutely necessary, because it's not going to be showing up on the screen except once every 60th of a second. And the last thing that I really wanted to point out was make sure you test fully. There's a couple of scenarios that you may not realize when you first start developing your application or working on Windows Vista. I mentioned this first point here earlier, that Windows XP driver model still works on Windows Vista. So don't assume you have the new driver model. Make sure your application works with the older driver model as well. Obviously test with the new driver model, because there are slight behavioral changes, and we'll be getting into those very shortly. Test with and without the desktop window manager. Those timing problems or timing issues that may have been crept into your code, the assumptions you may have made about how things happen, are going to be sometimes harder to track down. And also test in windowed and full screen, because there are slight differences between windowed and full screen. So with that, let's get back and start talking about the goals. We're going to talk about scalability and reliability. One of the things that has really changed significantly in Windows Vista is that the GPU is now truly a shared resource. We have the operating system and key components of the operating system built on top of the Direct 3D stack. We have the desktop window manager. We have the Windows Presentation Foundation. There are games out there that are using it. There are multimedia applications, workstation applications. All these applications are running potentially at the same time and being composited onto the same desktop. Or they're handing off in a nice seamless fashion from one to the other. At the same time, we have a sort of a different axes of, we have the multi-monitor support, we have mobiles. These sort of various scenarios put all sorts of demands on the underlying system. So it's become critical that the GPU be managed in a much tighter, much more controlled fashion. In previous versions of Direct 3D, an application could assume they had full control of that card. They had full access. Once they took over the video card, everybody else jumped out of the pool, and they could do whatever they want. That's no longer the case. We really have to make sure that things like the desktop doesn't go down because of another application doing something bad on the GPU. And so we've made some fundamental changes in the architecture underneath. So with that, I'd like to talk about the display driver model. What I have here is a slide with a diagram of the architecture, rough architecture, slightly different, slightly simplified, as well as some of the key points. And I'll talk about the various features that this enables. In this diagram, obviously, I have the graphics hardware at the very bottom. The kernel mode driver in Windows Vista is much smaller than it has been in the past in Windows XP. We've taken a lot of the things that used to be done in the kernel and used to be done in the driver and moved them into different places. First one being memory management, scheduling of the actual GPU has moved into actual system components. Now, these parts are actually interesting because, first of all, we have this really complex piece of hardware. If you've gone out and bought a really expensive graphics card recently, some of these are $500. They're on par with what an expensive CPU nowadays costs. And if you've looked at the previous programming models, it was kind of primitive because you had to do virtually everything yourself. Manage the memory, allocate it when something happened like a mode switch, or you've gone from full screen to windowed mode, you had to recreate all your resources, all that sort of stuff. So what we've done in Windows Vista is we've actually virtualized memory. That's the first biggest change. Your graphics card may have half a gigabyte of memory on it, but in fact the limit now is your page file size, because those resources are also virtualized the same way as they are in your CPU. So you don't have to worry about, okay, do I actually have enough memory on my card to fit this last texture on there? Other things that have changed is the scheduling of the GPU. We now have a multitasking scheduler so that not only can the desktop Windows Manager run, but other applications can run on the same GPU at the same time and share that resource in an effective manner. Now, for the reliability, as I mentioned, we've moved some of the kernel pieces out. You'll notice that there's this user mode driver that's really sort of part of this kernel mode driver. Well, used to be part of the kernel mode driver in the past. We've moved it up into user mode. And that's key, because one of the things that happens is your application, which is using high-level shader language or issuing commands to the GPU, the actual hardware has some native command stream that's different than what's actually being generated by the runtime, and there has to be a piece of translation code. So what that user mode driver does is does all that necessary translation for the hardware-specific pieces. Now that it's in user mode, what it means is when something bad happens, because drivers have bugs or your application may have bugs, at worst it can only harm that one application. It won't bring down the entire desktop. It won't bring down composition. That sort of change was very important. Another thing, fault tolerance, I'll touch briefly on that's happened, is we have a unique capability with the GPU. Unlike the CPU, when something happens to the CPU and the hardware hangs, usually your machine is dead at that point. Well, with the GPU, because it's actually a different card, it's a separate device, there's the potential to actually reset the hardware physically. So one of the facilities we've added into Windows Vista is to actually be able to reset the hardware so that if some application has done something bad, it has some bug, passed it down some bad parameters, it could even be the driver has done that, passed down bad parameters to the hardware, we can actually reset the hardware, bring the system back without actually interrupting the user experience. Now, there may be a slight pause, but at least the system comes back and is alive. The reliability aspect of that is just amazing. Now, with that, there's this other concept that we're introducing, which is managed primaries. The way I like to explain that is what happened in the past, and I don't know if those of you who have used D3D or have worked with the GPU a lot, you may have noticed that the window that actually GDI draws on, the actual back buffers that your application may allocate to do its rendering onto the screen, those things tended to be in a sort of a pool of, if you want to call it, and they were sort of shared amongst each other. So occasionally GDI, if you were actually rendering things to GDI, would appear on the screen in the middle of your application. If any of you have played games and wound up your Outlook flashing in the bottom of the screen, that sort of thing happened in the past. Well, what we've done with managed primaries is we've actually, when an application starts up, it gets its own surface now. GDI has its own. Your application has, when it's full screen, has its own. And that feature was really key in enabling us to do something, which is get rid of the device loss that those of you who have used D3D have experienced in the past. There are many cases in the older programming model where, let's say you've done an Alt-Tab and gone from full screen to windowed mode. You get back an error code from the runtime saying, your device is lost, you need to recreate all your resources. And the way we've dealt with it traditionally in the past, we've created things in managed pool, which allowed you to recreate quickly because you had a shadow copy in system RAM, and you could then download it to the card really fast. But, you know, large applications, especially CAD applications, which have multi-megabyte files, they may already be heavily memory constrained, or for whatever other reason you're memory constrained. Well, what we've done in Windows Vista is eliminated that. Because we've virtualized memory, because we have the concept of managed primaries, your application, when it is running, your resources are paged into the GPU. The GPU runs and does its work. As another task comes in, and if memory is needed on that GPU, those things are paged out and potentially out onto disk so that those resources never get lost. In fact, I'll talk about that in a little bit. Things like device lost, the only time you will actually get device lost is in the case when the hardware is actually crashed and we're resetting it. We'll tell you that something's gone wrong with the physical hardware, and we're bringing it back. Other things that we've changed are things like plug-and-play and rebootless driver upgrades. This is probably one of the biggest boons in terms of being able to change your video driver on the fly on your system without actually having to reboot your system. And then the shared surfaces and secure surfaces I'll talk about in a second. So those are sort of some of the highlights of the Longhorn driver model. Now, a couple of details I wanted to talk about in terms of the scheduling and the memory management. So this is the basic model of scheduling, basic model of virtual memory is going to be available in Windows Vista. The granularity of that currently when Windows Vista ships is going to be on a per resource granularity. And the scheduling that we're doing on the GPU is done in the software. What will happen shortly after Vista is we're coming out with the advanced model. The advanced model actually requires hardware support to do this, and there we'll have things like page level faulting. So CAD applications or applications that have very large data sets are going to be really interested, because if you allocate a multi-megabyte file that's a texture or a resource, you don't actually have to page the whole thing into video memory. What you'll do is you'll page only that section that you actually need to accomplish the rendering that's at hand. As well as the hardware context switching capability will allow you to actually switch threads in mid-stride. Today what will happen is once a task is scheduled to actually run on the GPU, it'll finish before the next task. Usually that's going to be quick, but the hardware context switching will even make it more responsive and better. So with that, let's talk about some of the subtle changes to the graphics stack in Windows Vista because of these changes in the underlying driver model. The first one is that you can't interleave GDI and D3D content anymore. Okay, that's probably the biggest one. You can't draw lines on top of your 3D content. You can't blit things onto that. What you actually have to do is you have to get the surface as a DC, and then you have to render to it with GDI, and then blit the whole thing. I don't know if how many of you are going to hit that issue, but in the past it's been very easy for an application just to draw its 3D content, and then when it wanted to put UI on top of it, it'll just draw UI. That was a very common practice. That just won't work because you don't have those synchronization mechanisms. I pointed out that GDI is software only, and the key being is that you will notice this in terms of performance, depending on how much UI or how much GDI activity you're doing on top of your D3D content. And then managed primaries, as I mentioned, the GDI pop and flicker that you used to see on your applications as your back buffers flip, that's no longer there. Now, the one thing I sort of forgot to mention as I've been going on, and please excuse me as I go back as I remember things I should have pointed out. All these infrastructure changes I've talked about so far, what happens is they're available to you in the new extended D3D9 for Windows Vista. So your applications that are written to D3D9 that's currently available through the DirectX SDK, those applications will continue to run. But we're going to emulate all the behaviors of the previous OSs so that your application doesn't have to change. If you want to take advantage of the virtual memory and not have to have a shadow copy of your textures and stuff in memory, you have to actually use D3D9EX, and I'll talk a little bit about that one. And then the last thing I want to point out, some people may have made this assumption in the past, and that's no longer valid in Windows Vista driver model, is the fact that the GDI desktop is no longer one of the buffers in your swap chain. So for example, a usage that an application may have made in the past is it's rendering its 3D content, it gets to the end and decides, oh gee, I want to print that out, or I want to capture it and mail it as a bitmap to somebody. And they may have just grabbed done a get DC, grabbed the GDI desktop, did a blit of that content into a bitmap and sent it away. Well, that worked in the past because GDI, the GDI surface was actually one of your buffers. Well, that won't work in Windows Vista because now the buffers in your swap chain are actually separate buffers from what GDI is rendering on. You actually can't interleave the two. So if you have that assumption, you will need to make some changes. So things to do. This list is actually probably fairly short. And the first one is actually kind of interesting, as recreate your swap chains if things change. Obviously, when your window gets resized, you want to recreate your swap chain because what happens is we'll typically stretch your application to fill the area anyway, but it will look better, it will be more performant if you actually resize the buffer. But the more interesting thing is that we've actually added pretty low down support in the operating system for rotation on the monitor. And if your application does nothing, rotation will happen for it. But the thing that you have to do is at least detect it. If the screen has been rotated, you should recreate your swap chain so that your actual app will also rotate as well. And then lastly, don't mix GDI and D3D content. Okay, so with that, I'm going to move on and we're going to start looking at D3D9, the extensions that we made to D3D9. A lot of these extensions are for reliability and scalability, and they're specifically used by services such as the Windows Desktop Manager, Media Player, and so on for the new capabilities in the operating system. So, as I mentioned, that for your D3D apps that you have today, like all your games and stuff, they don't have to change because we emulate the underlying behavior. The interesting thing is, they also get advantage of the underlying changes anyway, just by the improved stability of the driver model, by the fact that you can actually have multiple applications. So while each individual application today, for like today's technology, can't actually allocate more of the memory than what's on the video card because we'll artificially limit it, but the fact that you can have 5 or 6 of those applications all running and the memory is actually being paged in and out off the card allows you to run more D3D applications under Windows Vista than you would have in the past. So the takeaway here is Direct3D 9C or even older applications, they'll just work on Windows Vista. There's no change there. However, to use the new benefits explicitly in your application, you have to use D3D 9EX functions, and we'll talk about that on the next slides. First off, a lot of you will be going back home and start playing with Windows Vista and want to do some development. We have documentation in the Platform SDK for all the new APIs and extensions we've had. I'm just going to point out that the only thing we've changed, this is a little code segment that we've changed for D3D9, the EX function, is when you create a D3D9 device, you have to say you're creating a D3D9 for Vista device. On Windows XP, if you call this, or if you don't have the new driver model, you don't have a Windows Vista driver on the system, this call will fail, and then you can just create the older style device and not use the new features. If this call succeeds, then you know you've gotten a device that actually can use those new features. But to actually get at the APIs, you have to actually do a query interface and get the new interfaces for D3D9 that have the new functions and new extensions. Now, I'm showing you this with the note that this is changing in beta 2. Okay, we found that while this sort of worked and was a fairly simple way of actually extending the API for us to get the EX functionality, there were some issues, and we decided that after we got some feedback that this breaks a couple of people who inherited from our D3D9 interfaces. We're actually adding a new function in beta 2 that will actually explicitly let you create D3D9 EX, and we'll have documentation on that change later. Now, the other note I have here is currently the build you have does not contain D3D10, but we will be including that in Beta 2. So we'll talk a little bit about D3D10 later, and you'll be able to play with that after Beta 2. So let's now start looking at some of the API changes we made to D3D9. And as I go through these, what you'll see is that all these changes are really just exposing infrastructure changes in D3D9. We haven't done a lot of new features. There's a couple of new features here and there, but the vast majority of these things are just trying to expose the underlying architecture, underlying changes we've done. So the first one is being shared surfaces. Those of you familiar with D3D9's API set have probably seen the pshared handle on a bunch of these APIs. It wasn't used in the past. It was just there, didn't do anything. You typically passed in null. Well, now what happens is that handle you use when you actually create a resource. So a creating process can create a surface like a texture. It can mark it as shared. You'll get back a handle from the underlying system that now you can somehow, any way you want, pass to another thread, another process, and then you open that same resource. So for example, the desktop window manager uses this exact same mechanism for composition. What happens is your D3D app is actually rendering into a texture, and that texture is shared with the desktop window manager, who then takes that texture and composites it onto the screen. The only sort of caveats there is that only the creating process can actually lock that texture. So if you want to be able to read and write to that resource, that shared resource, only the creating process can do that. We also don't provide any automatic synchronization currently. We're looking at adding that in post Windows Vista. There are ways you can synchronize between a process, between threads and between processes, so that when you write to a texture, you can know that the updates have actually happened on a GPU and you can work with it from the other process. However, there's nothing automatic. So things like lock, you'll have to lock it and so on. And the other thing is that it must be pool default. Those of you who are familiar with D3D, pool default typically means that the driver is going to try and allocate the memory for that resource on the video card. And those are the only restrictions you have with those APIs. Now, this slide I included because it sort of could be confusing in documentation. One of the things that happened in Windows Vista is pshared handle actually got overloaded for a second usage. So while it's predominantly, and almost everybody's only going to use it for shared resources between processes, between threads, it can also be used to initialize a texture from a bitmap. Now, the reason it works is because the bitmap that you're creating has to be system memory. Well, system memory obviously can't be a shared resource. So if you put a pointer to a bitmap into pshared handle and call like create texture, it's going to assume that handle is a pointer to some bitmap that's of the right format to initialize that structure. There are certain scenarios where this thing was necessary for various Windows components, and we've exposed that to any application that wants to do it as well to initialize these textures. However, when you're looking at it, I know even after many months, I go back to the spec and say, why did we do this? It's sort of a little bit confusing on occasion. GPU resource management. I mentioned that we have threads and priorities. Actually, we have some pretty fine granularity and control. GPU thread priority, same as CPU thread priority. Actually, I believe even the values of the priority levels are the same. And we have the same sort of base priority with a priority that you can modify off that, exactly identical to the model that the CPU uses. So if you have a task that's using the GPU and you want to make sure you need that little bit of extra GPU resources, you can increase the GPU priority or decrease the GPU priority. Now, the other things that we can actually modify are things like when you create a texture or some other resource, we can specify the priority of that resource as well, so that the scheduler will try and decide, based on the relative priorities of all the resources in the system, what needs to be on the GPU at any particular given time. Right? And then residency check is also a really useful feature for those applications that want to know whether that resource that they're about to use has actually already made it to the card, because it potentially could be paged out to disk, or it could be in system memory, not yet on the card. So let's say that you want to have some texture being put onto an object, but if that texture actually isn't in memory yet, you don't want to stall, you're willing to paint it blue or something. You can actually do a check and do a different type of processing if that resource isn't on the card. So we have some pretty fine-grained resource management aspects. And then another change that we made, or this is probably one of the new features that affects the API as well as the runtime, is the fact that in the past, while you had absolute control over the graphics card, you didn't always know when things went to the screen. The Windows Media Player have been asking for the ability to tell, have we glitched? Is our audio now out of sync? How do we tell that I'm falling behind on my frame rate, or I'm getting too far ahead? That sort of thing. So what we introduced was this ability to actually ask for frame statistics. So when I actually go and present an entire frame to the buffer, I get in this API, I get a simple index number, a number telling me that this is present 5. But what I can also do is query now and say, what has the GPU actually done? Which frame has it actually presented? Is it the first one that it's now presented? Is it the second one, third one? How far behind am I? And so if you find that you're falling behind and you're actually asking the GPU to do too much stuff, you can actually start to eliminate frames so that you catch up. Or if you're finding that you're not providing enough stuff to keep the GPU busy, you can put more things. The sort of associated with this is the ability to do things like presenting the same frame twice. In the past, what you actually had to do was actually re-render the entire image to get the same frame presented. And places you do this is, for example, your monitor is running at 59.9 hertz as opposed to exactly 60, but you're presenting at 60. So every X amount of time, you're actually going to have to repeat a frame just to keep the frames in sync with like some other external thing like the audio. So being able to represent is a useful thing. All right. So let's talk about the subtle changes of all the things I've just talked about. First being pool default. Remember, the pool default in D3D refers to things that wind up on the graphics card. Those resources now never get lost. They're always there. Unless the physical card itself crashes, you don't have to go recreate the resources or anything else like that. You won't get a device lost. There's also no, quote, limit. So you're using the new APIs for Windows Vista, and you'll be able to allocate textures and other resources until you actually run out of page file. Device lost error is very rare now. About the only time you'll see it is when the actual GPU hangs for whatever reason. And we've introduced a new error code, which is device removed. When you actually do things like a driver update, you actually install a new driver, you'll get a device removed if your application is running. Most applications, again, will probably not see these. Some long-running applications, such as the Desktop Windows Manager, for example, will see these fairly often because they have to survive across an upgrade of the driver and then continue running. So they need to deal with those. Now some unsubtle changes. Those of you who are currently using D3D, things like test cooperative level will now always return OK. This has changed from previous versions. We've replaced it with a new API called check device state. And the reason we did that was because we've introduced some new device states. And we wanted to make sure that you didn't actually miss it anywhere in your code. It's just so easy to, because the APIs between 9EX and D3D9 are so similar, it's very easy to miss certain things. So what we've done is we've introduced these new device states. Device lost is, it was there before, but now its meaning is really different. What it means is the hardware hung. It's coming back. Device hung is a new error message. Specifically what it means is that your application caused the hardware to hang. And if you do it again, it's going to hang again, most likely. So if you ever see a device hung, you may want to do something different. Device removed I talked about. And the last one, present mode changed, isn't actually currently implemented in the current builds. That's going to be coming in beta 2. But the new success code, present occluded, is actually a new addition. With the idea of composition, with the managed surfaces, with all the infrastructure changes, one of the things that can happen is you may actually not be rendering on the screen. You may be using the GPU for something else. You may be calculating something rather than actually rendering. So the present occluded just means that, yes, you did your present, yes, the GPU is doing stuff, but we're not showing anything on the screen because either your application is minimized or a full screen app has taken over the screen and we're no longer drawing. So if your application is using the GPU for something other than drawing on the screen, then you can ignore this success code and just continue on. However, if you're actually like a game or a CAD application, you were actually drawing images, you probably want to stop and wait for that occlusion to disappear so that the activity you're actually burning the GPU on isn't wasting GPU cycles. So that's sort of a new use. And again, it's part of the fact that the GPU is now a shared resource. It's now used by multiple applications. Somebody else may be actually on the screen and you're just not visible. So with that, let's talk about when you would use the new Windows Vista Direct3D 9EX APIs. Obviously, you can use the current DirectX SDK. You can build D3D 9C applications today. They will run on Windows Vista with no problem. Some classes of applications like CAD may want to eliminate the memory bottleneck. Use the virtual memory system. So you'll be interested in using the 9EX functions for that. You may actually want to be able to share resources between threads, between windows, between monitors. For example, let's say you have a texture that you use on a button or a bitmap or something fairly often. And if you're a multiple head application, you're going to wind up creating that texture multiple times because you have to do it per device. Well, you could actually now create it as a shared resource, have it exist only once, and use it over and over again and save that memory footprint. That can be significant if the texture is huge, especially like we're talking about the design or heavily graphic-intensive applications. There are certain scenarios where you may actually want to control the priorities of your GPU thread or the priorities of your resources. Now, I'm going to caution you that use resource scheduling like the GPU thread priority and the priority APIs sparingly because they will affect other applications. And again, if everybody starts using them, it's just like on the CPU. If everybody runs that real-time priority, well, then it's probably no better than it was before. So use it sparingly. And then some applications who want to have the best Windows Vista experience and are willing to have multiple code paths, because that's actually an interesting thing. You will want to write your application so that it runs on Windows Vista, gets the best experience on Windows Vista, uses the 9EX, D3D 9EX APIs on Windows Vista, but you still probably want to run your application on WinXP and so on. And so for those cases, if you're willing to write the multiple code paths to fall back to a reduced set of the API set, because the 9EX is really an extension, you should use 9EX. Or some classes of applications may only be targeting Windows Vista. In that case, if these features are useful to you, by all means, go ahead and use the 9EX. So things to do. Obviously, use D3D 9EX on Windows Vista. Use shared surfaces to limit the memory usage. Always use pool default rather than pool managed when you're using the new API. It'll save you memory. There's no need for actually, it'll also save you CPU time, because one of the things about pool managed is the D3D runtime is going to do work in the background to make sure that those backed up system images get moved into pool default. Well, there's no reason for it because those pool default ones never disappear anymore. You don't lose them. Watch for device removed messages and do the appropriate thing if you're a long-running app. And don't use explicit resource management APIs if your scenario doesn't actually warrant it. For some reason, every time I look at this point, I think of my mother saying, "Okay, now children, let's use the GPU. Let's share the GPU," But I guess it's just my sense of humor. And also limit your GPU usage if you're in window mode. If you're occluded, you're getting present occluded, stop rendering if there's no point to it. Don't render more frames than will actually appear on the screen, those sort of things. So they'll just be good citizens on Windows Vista. Okay. With that, I'm going to move on to talk about D3D10. And here's where sort of the organization of this presentation was difficult. Up until now, what I've talked about is infrastructure changes, D3D9, which exposed most of those infrastructure changes in the API effect. So, and most of that was focused on stability, reliability, the shareableness of the GPU. Now, D3D10 is also built on top of the new architecture, the new driver model, and requires all that. But here we're really focusing on the new capabilities of the GPU and the new capabilities of next generation hardware and the things that it can do. And as I mentioned earlier, in the next presentation, we're actually going to be doing a particle system walkthrough. We're going to be looking at code on using D3D10. And my colleague Sam Glassenberg is going to be doing that demonstration. So let's look at what D3D10 is about. It's a fundamental change in the way D3D works. This is a pretty big change. So in the past, we've done sort of incremental changes. We've added extensions from 8 to 9 and so on. D3D10 requires Windows Vista. It requires new hardware. It requires the Windows Vista driver model. All future versions of D3D9 will be based off of D3D10. So while we may add incremental, very minuscule changes to D3D9, all the innovation we're doing in the 10 API set onward. Now, for the last, I don't know, Sam can probably tell me how long, we've been working on D3D10 with the IHVs and our partner, getting feedback from ISVs. So the actual API set that you'll be seeing in Beta 2 has gone through a lot of back and forth between the IHVs and the ISVs and ourselves. So with that, let's take a look at what some of the changes are. So in the past, D3D9, for example, we had devices, we had presentation, we had buffers, we had all the various things that were related to the hardware also intermixed with the actual rendering. What changes in D3D is we introduce a new layer called DXGI, which is the graphics infrastructure piece, which is separate from the APIs that are related to rendering and drawing and actually sending commands to the GPU. The thinking behind this is that one of which is that we're going to want to rev D3D in a much faster time frame than these other things like managing the monitor, managing the actual adapters changes. Those sort of things should be pretty well stable. The only time they probably change is if we actually change the device driver model again or extend the device driver model. So that's probably one of the first big change. And this allows us to isolate, and it potentially will also allow us to do some level of sharing of resources between future versions. So for those of you who are building components, this may be actually interesting for you. You build a component with D3D10. Potentially, you can actually share information between the component using D3D10 and the component using D3D11. That sort of stuff. So let's take a look at the hardware, the new hardware pipeline. I'm assuming since most of you have used D3D and have a good background in computer graphics, you've seen this diagrams very similar to this, which is the pipeline architecture. So the two green pieces, or the green pieces, are the pieces that are new in the model for D3D10. The input assembler, which is at the top, has sort of been implicit in previous models for D3D9 and so on. It's now been made explicit in D3D10. And the other piece is geometry shader, which I'll be talking about in a little bit. Now, I'm really just going to start at the top of this list in terms of the features and the capabilities and start talking about it. The first biggest one is that there's a guaranteed feature set. In the past, some of you have probably had experience where some particular card out there, your application needed a feature and it just wasn't there. You don't have that in D3D10. All features are required across the board. All vendors will support them. So there's no caps. You don't have to look at capabilities. The other change is that the behavior of that hardware is extremely consistent. There's a very large spec in terms of the tolerances and how each function behaves. These are fundamental. This is really a shift in D3D. In D3D in the past, we've had, exported capabilities if enough of the hardware vendors had it. Now what happens is all the hardware is going to be very consistent. I mentioned the two new components, the input assembler and the geometry shader. There's also the concept of a common shader core, where these shaders actually have very, very similar instruction set. So this is a pretty big boon for the IHVs, because they can actually now balance across these various shaders. If they need more geometry processing, they could potentially have more geometry processing units. If they need more pixel processing, they can actually do more pixel sort of things. And then I'll talk a little bit about the stream output and resource on future slides. So let's drill down into some of the points. For the rest of the slides, I've sort of picked some high-level items to talk about at random. What we can do is, if you have questions further on, we can either answer them after the presentation, or both myself and Sam will be in the lounge area, in the presentation lounge. I'll be there on Thursday. Sam will be there on Friday. So feel free to drop by, and we can chat about the various changes. So one of the things that struck me when I was putting this deck together is that in D3D10, we can actually take resources like a cube map, and we can actually have a view onto it that's different than just being a cube map. We can actually look at it as if it was like 6 different surfaces. All right? And that allows us to do a bunch of things. We can reuse it in various stages of the pipeline. We can use it as output in one set, and then go back and reuse all those textures as something else in a different set. And I'll be giving an example in a couple of slides. The geometry shader works on, which is the other big component change, it uses entire primitives. And in fact, what it does is, so the vertex shader, while it worked on things like vertices, pixel shader worked on pixels, the geometry shader works on the entire primitive and has a bunch of information about that primitive. Things like, what are the adjacent vertices to that shader? You can tag that geometry with information. You can tag the vertices. You can insert new vertices into the stream. There's a bunch of things you can do. You can compute things about the geometry in the geometry shader. So this is really a new stage that will enable new capabilities in the hardware. So one of the examples I'm going to show you here is the single pass rendering to a cube map. So for example, like a cube map is used typically to map your environment. And if your environment is static, you can pre-calculate it all at the beginning and everybody's happy. And you can, like in this picture below where I have this spherical ball, what I can do is, if this was all static, it's not a big deal to try and figure out how to map that environment from the cube map onto that sphere. But what if your environment is animated? What if there's objects moving through it? Well, typically what you'd have to do is actually go and build this cube map for each and every object that's dynamically moving around. Well, what's really bad is if that object happens to fall into multiple faces of that environment map, you may have to do multiple passes through to do that. Well, in comes the geometry shader. What the geometry shader can do is actually do things like tag. Like let's say we have a triangle. It can figure out which one of those faces of that cube does that triangle appear on. And we can tag that triangle in that geometry and pass it further down the pipeline. And then when I actually go and render that triangle onto, I can actually render it to all 3 surfaces in one pass at the same time, rather than having to do like 6 passes or however many is necessary to do it. This sort of thing gives us big speed improvement. So let's take a look. Now what this is an example. And so the animated piece is this thing swirling around the ball. And what we're doing is in one pass generating the cube map. This is actually a video. And this was built with D3D10. And now, since hardware currently isn't available for D3D10 class hardware, This is actually being done through the software rasterizer. It's an emulation of what the hardware would be like. But the idea here, what I wanted to show you here is that D3D10, the API is stable enough. The actual implementation of a software version of the hardware is far enough along that we actually test and build samples and verify that the concepts and everything work the way we expect them to work, that we can actually show you a video. Okay. Another interesting feature in D3D10 is this idea of stream out. So I talked about the geometry shader, the fact that I can do modifications to my geometry, potentially insert vertices and create new geometry. What I can also do is I can do stream out, which is as my geometry comes through, I can actually write it out and feed it back into the pipeline itself and do an iterative process with it. So I can do it to one or more buffers. I can then, once I've had that streamed out output, because I may be adding information into my output stream, I really don't know how big that buffer is anymore, right? So in the past, what you would have had to done in older APIs is actually read that information back to CPU, figure out how big it is, and then do a separate draw call. And there's this big round trip back and forth between the CPU and GPU. Well, now what we can do is actually feed it back into the pipeline and tell the GPU just to deal with how much data is there. Do an auto draw. You know, if you've added 1,000 points to the geometry, it's going to deal with it. So you can do it for things like skinning, morphing, render, do the calculation once, render it many times. Or you can do it procedurally where you're actually generating something like a vine-like spaceship that sort of grows. Actually, that's sort of what Sam will be showing with the particle system demo, where he's going to do fireworks, where he's doing some of the calculations are physics-based calculations, generating explosions and so on, calculating lifetimes, projections, and so on. And those are the sort of things you can do. And now you can do them all on the GPU. So what the CPU is now doing is worrying about things like, when do I need to get that on the screen? How many frames a second am I doing? And worry about higher level things. And then the last thing I'm going to talk about is predicated rendering. And I sort of alluded to that with the auto draw. But what you'd like to be able to do is, based on some result that's happened on a GPU, actually decide whether you're going to render something or not without having to go back to the CPU. Right? Because as soon as you have to cross that CPU and have the CPU make decisions, you have to synchronize with the GPU. You're going to maybe slow down and wait for something to finish on the GPU before you can issue the next command. And that sort of stuff just gets in the way of your frame rate. So what we can do is this thing called predicated rendering. So to give you an idea of what it looks like is, here's we have a city scene, and in it we have this fairly complex monster, getting ready to smash down Tokyo or whatever city this happens to be. But we don't really want to render it if it's hidden, right? So what we can do is actually the bounding box. We could render the bounding box and find out, is that bounding box hidden? If it's already hidden, then there's no point in even drawing the monster, because the monster must be hidden. And so we can wind up doing all that on the GPU without having to come back to the CPU and actually render that thing. Okay. So in summary, let me go back, because I've covered, as I said when I started this talk, a wide variety of things. We've talked about the infrastructure in Windows Vista. We've talked about the changes we made that are necessary to make a really reliable, robust application, as well as OS components on the system. And this is what the Windows Vista driver model was all about: the virtualized memory, the scheduling, and so on. We talked about the various technologies, because none of these things are independent technologies. They span things like the driver. They span the IHV. They span the scheduler and the kernel. They span the D3D APIs. They go up into desktop composition engine and Windows Presentation Foundation. All of these pieces have to work in concert. And then we talked about all the various things you as an application developer have to worry about. Things like, remember, when you're in a composition world, you're only being displayed at once every 60th of a second, so don't render too many frames. The GDI doesn't is now in software, that you can't do GDI calls on top of a D3D surface. All these things you're going to have to keep in mind. And then we also talked about future, what's coming down the pipe. We have D310 also in Windows Vista. Next generation hardware will probably be there at about the time Windows Vista ships, and you'll be able to use some of these D3D10 features with that new hardware to do even more fantastic things. So with that, we're going to be, after this presentation, I'm going to open up for questions, and after this presentation, those of you who are interested in actually seeing code samples, we're going to go into the next room, which is right across. I think the people who scheduled this conference hall wanted to make sure we got our exercise, and we all got up and took a little walk. So we'll be actually next door. And in that, what we're going to cover is I'm going to cover, during the first part of that talk, we're going to build some shaders, some vertex shaded pixel shaders using current D3D9 technologies on DX10. We're actually going to build a globe of the Earth. We're going to start with a sphere and build it up in various layers, and we're going to texture it, we're going to light it, we're going to do all sorts of things. And then Sam's going to take over from that point, and we're going to show you some D3D10 particle systems and so on. So in terms of resources and where you can go right now today, we have a forum on Microsoft.com for direct 3D questions. The current DirectX SDK is integrated with Visual Studio 2005, and feel free to send questions. So with that, I will open up the floor for questions. And oh, by the way, they've told me to make sure, fill out your eval forms, hand them in. And if you wouldn't mind going to the speaker if you have a question, or a microphone if you have a question, so we can actually capture the question.
You mentioned that we won't be checking for caps anymore. Now I can imagine two scenarios. First of all, the one where I'm worried about swapping between virtual memory, so probably my chips that are not on the graphics board and the graphics board. And so I'm really wondering how big is this texture that I'm going to load, and how big is my real on graphics memory board memory. And the second one, as soon as graphics card manufacturers create new cards, they will be probably adding extra features. So I'll be starting to check caps again.
Okay. So your question is really two parts. One is really how much can I actually know about the hardware and so on. So for that part, there's really two answers. First of all is the advanced model, for example, we're going to have page level faulting. So in terms of needing the whole resource in memory at the same time, that probably won't be necessary. What you do in the advanced model is just load in only those pieces necessary to do the particular task at hand, and the scheduler will manage that. Again, you're giving up some bit of control in terms of, you had in previous versions of D3D in terms of getting it onto the card and knowing it's there and working with it. But now the whole system as an overall, it's now sharing that. The second question was about graphics manufacturers wanting to have new features and so on. That's really one of the reasons we're thinking that we're going to be moving ahead with versions in a quicker fashion, so that we actually hope to stay ahead of the industry in that. And D3D11 will expose across the board new capabilities. And so what you'll be looking for is maybe one cap. Is it D310, D311, so on.
Okay, so I'll be checking for the version of DirectX.
Effectively.
Okay, it's effectively the same.
Yep. Unless Sam has anything to add.
Well, I think there's a difference between having to query for each individual format supported, and the hundreds of caps that are there, whether you support power through textures.
Of course.
All these little subtle things, any combination of which can be available in any piece of hardware, as opposed to the model that we're moving towards. Oh, great. As opposed to the model where we're moving towards, where you're going to be checking one cap, and that one cap is going to tell you whether you have this whole slew of features, and you're going to have a guarantee that any piece of hardware that supports that cap is going to support the whole slew. So it's going to be incremental. It's just when you actually, when you want to take advantage of something, you don't always have to have a software fallback for any combination of cabs.
Sure. But then again, as soon as you start pumping out a lot of new versions of DirectX, we'll be getting there again, but just in a few years.
Well, what's going to happen is, just with anything, you're going to have sort of a generation of hardware. So, temporally, there's also going to be different, performance is going to improve exponentially with these chips. So you're going to have to, support some performance window. But what this basically means is, hardware that's going to have similar performance is now going to, that's going to be of the same generation is going to have the same capabilities, as opposed to now where it's sort of all across the board. And it's going, it's not going to be like, the consoles where once every 5 years you get one piece of hardware, but it's going to be a little bit more like, okay, once every 1 year you have a solid feature set, something like that, as opposed to this, this scenario where we've seen previously, where there's any combination of capabilities that a card could choose to support or not support.
Okay, thank you.
You talked about the need to throttle the frame rate. Is there a suggested way to do that? So should we be using the VBlank or the frame statistics you were talking about, or querying refresh rate, or assuming a 60 hertz cycle?
Yeah, I believe it's documented in the SDK documentation, but it's just use the default, when you do the present, have it present on default. That way it will actually sync up with once per frame.
Okay.
Your present call will wind up blocking in that case and won't come back, so you keep that in mind when you're dealing with it.
My question may not be directly related to DirectX, but what is going to be the level of support for OpenGL in Vista? Can you touch on that a little bit?
Okay, so the question about what's...
And not just OpenGL, but things like CG from NVIDIA, let's say.
Okay, well, Windows Vista is the same as Windows XP in these terms. It's an open platform. People build applications, add extensions. In Windows Vista, we actually have sort of 3 levels of support for OpenGL right now. We have the software version, which we've always had. Some of you may have actually heard we're actually going to be shipping a 3D translator that translates GL to D3D. That's in the box, so that if you just install Windows Vista fresh off the machine, there's at least some support of hardware acceleration, as well as the hardware vendors are capable of writing their ICDs and using, making an OpenGL application as well. Now, right now, the one thing, there's one caveat right now, which is that you'll see it in your current beta. If you actually manage to get an ICD from a IHV third party, there's certain features in OpenGL, the same as in DirectDraw, that for compatibility reasons, the desktop composition turns off. We're still talking about potential solutions with the IHVs about how we could make that work. Right now, that's the behavior in the box. So the choices you have are software. There's the D3D translator, which works well with the composition engine because it uses D3D. And then if you want the full power of the CPU and full compatibility, you can get the ICD from the vendor, and that works as well.
Well, in a nutshell, it won't break existing applications, OpenGL applications.
Pardon?
It won't break the existing OpenGL applications.
Back compatibility and upward compatibility is one of our big goals. It will really depend on the vendors and how their ICDs are written.
Thank you.
Yeah, I actually have a continuation. It's a continuation of the previous question. You mentioned that there is some OpenGL functions or features that will disable the desktop composition. Is there a list somewhere available that shows that list what those functions are?
So the question is there a list that shows what disables desktop composition? I have a short list in my email right now. I haven't actually published it anywhere. It typically has to deal with actually accessing the front buffer or trying to do something along those lines. So like in DirectDraw, if you try and draw on the screen without a window, or trying to lock the front buffer, OpenGL's read and write pixels, that sort of thing are and there's other things, but I don't have the complete list offhand.
Okay, thank you.
Yes, hello, good afternoon. Scott Fulton with Tom's Hardware Guide. You mentioned at the, earlier in the talk that a developer would be assuming a direct 3D10 library. would be able to assume a basic hardware platform that vendors would have to meet those specs, and that Vista would have to be installed, not XP, in order for Direct3D 10 to work. Could you give me an idea of the type or level of PC that a developer can expect his client or his customer to have in order to run an application that takes advantage of Direct3D 10?
I think I'll ask Sam to answer this, since Sam's the Direct3D 10 PM. He can probably answer this best.
So the question is, Direct3D 10 developer, what is the hardware configuration?
What the basic reference platform that a Direct3D 10 developer can expect his customer to have?
A Direct3D 10 GPU, and on top of that, it's basically, I guess, the graphics card is, I guess, somewhat orthogonal to any other features. I guess that's sort of up to the hardware vendors and what requirements they have on their systems for installing their D3D10 parts.
Well, is there any when you say Direct 10 GPU, I mean, we're not leaving it up to NVIDIA and ATI to decide, are you? I mean, aren't we talking a certain memory capacity, graphics memory capacity?
I know the D3D10 spec has a requirement. So in terms of like actual features so you're talking about the GPU specifically, or just the box itself?
Well, let's start with the box itself.
So the box itself, the requirements to instantiate a D3D10 device are a D3D10 GPU running a Vista machine with an LDDM, with a VDDM driver. As far as
you're saying there are no memory requirements.
There are on-card memory requirements in the spec. I don't recall exactly what they are right now. I can follow up with you on that.
Okay. Is there any places where they're published online?
No.
Do you know? Okay. Thank you.
I have a continuation from the OpenGL discussion. If there are these different models available, software or the wrappers around D3D or the ICD from the hardware manufacturer, is there a way to specify in your application which one you would rather load? So for instance, if the IHV driver is going to make the DWM punt, it would be nice to maybe not specify that or to specify a different route in some cases.
Yeah. In beta 1, it's possible. It's not easy. We're expecting to fix that and make it easier in beta 2. Right now, it's really about how the pixel formats are oriented for OpenGL. So those of you who use OpenGL, what happens is we actually order the pixel formats when you do a query for one. The first one you'll get back is the IHV ICD one. Next, you'll get the translator, and then you get the software third.
So we'll be able to query what's out there and then pick the one that we want.
And pick the one you want.
Okay.
Yeah.
Thanks.
Hi. GPU resource paging does not big impact to the system memory.
Pardon? I didn't quite catch that.
GPU resource paging does not big impact to the system memory? No?
It'll depend on your usage of the GPU, and the same as anything else.
For example, already we have a huge memory in the GPU.
Right. Yeah. Typically, you'll have like 256 meg or half a gigabyte on the card. It's really going to depend on the mix of applications you're running, what your application, if you're running CAD applications that have multi-megabyte textures. Hopefully, the situation with the virtualized memory will be better than it is today, because you don't have all these shadow copies, and the management of it is easier. So I think we're just going to have to measure that. I don't believe that it's going to be any issues or performance impacts there, but we're going to have to measure that one.
Okay, thank you.
All right, with that, thank you very much, and we're all going to head next door and do some demos.